So, do you know what supervised learning is? Okay, can you just tell us what it is? Like, your little idea, just bring it out.
Still have to, from time to time, still have to put in data about the level prediction.
Into more staffs because it doesn't know the answer. That sounds correct. Then reinforcement learning. That's something else. Let's not really about it. I'm sure you know what reinforcement learning is. Yeah, you know. Do you know what reinforcement learning is?
Because like
Okay, okay.
like if you are exposed to a particular experience over time,
Yeah,
then you will learn.
yeah. So that was reinforcement learning. In the sense that, in the second sense that you have an agent. Okay? So the aim is for the agent to learn on its own. Like you are not giving it examples and giving it answers. And you are not just giving it examples and asking people out what the answers are. Also. So you are exposing that agent to an environment and making that agent to interact with the environment. So there's an environment and there's an interaction between that agent and the environment in such a way that that agent will take actions, right? And the actions it takes will determine, will determine the state of the environment that it will be in. Okay,
I want to see if I'm still connected. I'm still connected now. Are we back online?
So,
Good.
first of all, it started with this guys. So one, Mark Monroe and Walter Pitt. So they were the first guys to bring
This page
computational
too wide.
So they were the first guys to bring about to relate neuron of the brain to artificial neuron. I don't think that.
A little.
You can see now. I just want to go.
Tayo. Just
The
look.
body.
Okay, no. That's
How about
better.
noise?
It's better.
How about noise?
So look at it.
So
This is better, yeah.
can you see? So they were the first guys to relate neurons of the brain to Boolean gates. So in this gate you have what we have your and you have your off, you have your negative gate, negation gate, and some other stuff. So all this stuff you guys are familiar with and or and negative gate, right? Okay. So you will get to know about them probably by the end of the class. So they were the first set of people to relate the basic, the smallest. They were the first guys to relate like the fundamental cell of the brain, which we call neuron, to computational thinking. That is artificial neuron. They were the first guys to bring about the idea. Then we have another guy called Frank Rosenblatt. He was the first guy that actually made the first artificial neuron, and he called it perceptron. So perceptron is like artificial neuron. So it was this guy that invented perceptron, and it was the same guy that also brought up the idea of learned weight. We'll talk about that later. Then when Frank Rosenblatt invented the perceptron, he solved a lot of problems. He solved a lot of Boolean operations like and or and some other stuff. But he was unable to solve a problem which we call XOR problem. So this problem was like a major problem in computer science. The perceptron was unable to solve XOR problem. And what actually led to this idea was this guy, Marvin Minsky and Sigmund Pepe. So they wrote a book called Perceptron to exploit the limitation of perceptron. So they all say that perceptron is good, it could do a lot of stuff, but it could not solve all problems. And this all because of this statement alone they did, it kind of made the research, it kind of made the funding into AI with respect to neuron. It kind of brought the funding down because people are like, if this thing cannot solve basic problem like XOR, so why are we spending so much time on it? So AI for like 10 years experienced what we call dark age, which is what we call AI winter. You get to know about this stuff with time. You keep reading articles, you get to know about AI winter. So it was like a 10 years window whereby there was no significant work being done on perceptron. So while all these things were happening, this guy called Jeff Hinton is regarded as the model godfather of is regarded as the model godfather of AI. So this guy is the great grandson of George Boole, which is the guy that brought up the concept of Boolean gates. Makes sense, right? So he's the great grandson. So technically he has like how would I say, he has like he has like being elegance. He has like elegance in his gene. He's supposed to do something because he said something like by the age of 9 he just felt like he's supposed to have like a PhD in something because of the family background he's coming from. So, you know, when you have like great person in your family lineage, you want to do something great. So that was like one of his motivation. But still does not really know what he wants to do with his life. So he all started with carpentry, then he went to physiology, then he went to psychology, then he went to computer science, then finally he arrived at his local minimum, global minimum, which is AI. So that was where he stopped. So while he was doing this stuff, he went to he's from the UK. Yeah. So being from the UK, there was no much research being done in artificial intelligence. So he needed to go to the US. Then he went to CMU University. That's this guy's university. CMU University. So not just CMU, he went to a couple of other universities. But while he was in US, he felt like, well, in as much as there's a lot of work being done in artificial intelligence, but this work are being funded by the US military. So he didn't really like the idea of building something that at the end of the day, it is being used not for the betterment of humanity. So this is something that we should all, somehow we should all like, whatever we are doing, we should ensure that whatever we are doing is adding value to humanity. Not just negative, not just value, positive value. So he felt like working with the military doesn't really go well with his morals and his standards. So he needed to go to Canada. So he left the US, then he went to Canada. So when he arrived in Canada, that is where he met like the Canadian government. They welcomed him because they like, till now they still welcome a lot of people. So they like the idea of people from different backgrounds coming in to do some stuff. So that is where he met this guy, Yoshua Benjo. He met Yann LeCun. So Yoshua Benjo, Montreal University. Yann LeCun was the first guy to use CogNet, which we will later talk about for hand recognition, MNEST for hand recognition. Then Yann LeCun, okay, this is Yann LeCun, okay, all together, this is Yann LeCun. So Yann LeCun is the first guy to use CogNet for hand recognition. Yann LeCun is currently the Facebook AI director. So 3 of them are regarded as the godfather of AI, but this guy is like the godfather. All of them are just sub-godfathers. So that's just it. So after while all these things were happening, before they started happening per se, we have this guy, Wagner. He did something called, he was the inventor of SVM, which stands for Support Vector Machine. SVM, I must say SVM is pretty powerful algorithm. It could solve a lot of problems, but it could not solve all problems. So that was where, after the whole AI winter, some stuff started happening. That is when we started having big data. We started having what else? Power. Handwriting is horrible. Just bear with me today. So, what's that? So, yeah, okay, this is where we stopped, right? This is where we are now. So, the all problem was still there, but what actually happened here was that they discovered that for you can't use just one perceptron to solve the all problem. For you to solve this all problem, you have to like stack couple of perceptron. When you stack them, that's where we come about the idea of multiple layer perceptron. By stacking them, you could solve the all problem, XO problem. So while all these things were happening, they had the idea, but they didn't have enough data to train the algorithm, and they didn't have enough computational power. So they needed to wait for the data to show up. Thanks to the internet, the data showed up. Then thanks to gamers, so thanks to gamers, you have like people like NVIDIA, you have people like AMD, Intel, and some other guys. They kind of invested in computational power, and both of them work together to ensure that you can train your algorithm with data, and with the availability of computational power, you can make your algorithm powerful. So thanks to these two stuff, it changed neural network. So while all these things were happening, let me just go to the next slide. So while all these things were happening, so I've talked about perceptron, I've talked about criticism of perceptron. This is the awkward AI winter. So while all these things were happening, a lot of kind of buzz in AI, like, oh, deep learning can do this, deep learning can do that, but it didn't really make any much difference till 2012. So in 2012, student of, not just student, PhD student of Jeff, we have about, we have about two, including, about two. We have Eli Saskova, then you have Alex Keshowski. These two guys were the PhD students of Jeff. So they worked together and they participated in this ImageNet competition. This ImageNet competition is a competition whereby every year they bring different algorithm to. There's this data set about 1.2 million images of different classes of pictures. So they are supposed to like see how powerful the algorithm can classify those pictures. So they use this ImageNet. They applied AlexNet on ImageNet. Then the performance was quite astonishing. So this was in 2004. In 2012, a lot of stuff actually changed. And Google Brain, that was when Google Brain came in. I don't know, I mean, if you know about Google Brain. Google Brain is like the part of Google that is in charge of AI. So currently they have changed it to Google AI now. So I think they have Google AI, they still have Google Brain. Or Google Brain is on. The Google Brain team is under Google AI. So that is just what actually happened. So they all, Google took Eli Saskova, took Alex Keshowski,
Alex
Chevesky. So that one is another story for another day. So they took in three of them. They worked on so many projects: Google Translate, Google Assistant, self-driving, self-driving car. Should I stop again? Like almost all Google products now are AI products. So he worked in a couple of projects. So that is just what has happened. So here was like the defining moment whereby they applied covenants, and ever since then it has been going up, and we don't know when it's going to come down because it's changing a lot of industries. So that's just brief talk. So starting from perceptron, then they criticized perceptron because it could not solve the X or problem. Then we had the concept of backpropagation.
What's the XOR problem?
XOR problem. We'll get to talk about the XOR problem. So then we have SVM came in, it was performing well, but could not really do much.
How do you think SVM solved the XOR problem?
Yeah?
How do you think SVM solved the
Hyperplane.
Okay.
So, and then you have this guy Leon LeCun in 1998, hand recognition using covenants. Then you have restricted Boseman machine, it's by the same guy. Then somehow they applied covenants to ImageNet competition and took the competition to another level. So that's just it. So the question is, why deep learning? Like, from what we have learned so far, from the linear regression we have done, from the logistic regression we have done, you will realize that most of this stuff you have to like add, you have to like code the picture. Like you have to like ensure that you fit the right picture in. If you don't put the right picture, your model will not work well. So with deep learning, what you just have to do is you take in the raw inputs. You don't necessarily have to like do any pre-processing. You take in the raw inputs. It is left for the neural network to extract those features to make sense of them. So, like for this instance now, if you are going to recognize someone's face, like I know that Pedro is sitting down here. So low-level features like lines, edges, a face is circular or rectangular or hyperbola. Then we have to like take in like middle level features like eyes, nose, ears. Then when we combine all these features, we can make sense with what the facial structure really looks like. So this is what deep learning does. You don't necessarily have to like apply any feature extraction. It does that by itself. So why is deep learning having great impact in the world? One of the major reasons is because of massive data. 90% of the world's data was generated over the last 2 years. That means we are churning out a lot of data, and because of the internet, that is why we are churning a lot of data. Not just the internet, because of the fact that we all have mobile phone. So mobile phone has brought a lot of people in. And also we have model algorithm like, you have like LSTM, you have like, I don't even know how to, you have like so many algorithms. Then computational power, you have your GPU, thanks to NVIDIA and some other guys, AMD, working on. And lately, Google released their current processor called TPU, which stands for Tensor Processor Unit. So I don't know how many of us are following in that. Yeah. So as of yesterday,
you get the TPU, you get
yeah.
everyone get the TPU.
As of yesterday, the guys that showed up, that participated in the program, they all got free TPU subscription to do their AI research work. So you guys are here listening to me while you're supposed to be listening to TPU. So alright, so let me just talk about, let me kind of digress, let me do something else. So this is how many of us know about NIPS? So NIPS is like Google I/O for AI guys, or it's like F8 for AI researchers. How many of us know Google I/O? How many of us know F8? So first of all, let me start with Google I/O. Google I/O is
How many of us know PyCon?
how many of us know PyCon? So Google F8 is sorry, it's Facebook F8 / Google I/O. These are like conferences whereby they get developers all over the world, from different parts of the world, just for them to like stop by and talk about what they have done lately and how the new Google product is going to affect their work and how they can improve on it. So they are developers. So they influence in and out of what you do
with respect to your app or with respect to Google product, how you use them. So they tell you, like, they give better insight of how should implement this product. So let's go back. So NIMS is like the Google I/O of AI researchers. So here you have like the best AI researchers all over the world. They come in, especially I think the conference holds in Montreal, Canada. So they come in to talk about their work, their papers, because they like to brag about themselves. The bulk of, according to what I heard, but I don't know how true it is, about either 15% or 10% of papers being accepted by NIMS are from Google and Facebook. So Google, I'm talking about both Google Brain and DeepMind. I'm not just talking about why Facebook. I'm talking about Facebook and FAIR, which stands for Facebook AI Research. So about 15%. I'm not really sure about the figure. So this gets to tell you that most of the work are being done by these two guys. Because of what? Because they have data. And computational resources is not a problem to them. Because when you have data, when you have money, you are God. So to cut the story short, so this is just a graph that shows you how the conference registration. So it's all the while, a lot of people, the way it has been following a normal trend, but in 2017 something happened. So the graph kind of went up exponentially. I don't know, but something happened. So this gets to tell you that a lot of interest, a lot of work has been done in AI, and it's kind of all of a sudden people became interested. They all wanted to attend the conference, all of a sudden. So then NIPS kind of they replied that in 2018, Singularity happens in 2018, which is where we are. So in 2018, what actually happened was that under 11 minutes, the conference registration was sold out under 11 minutes. So like having like Whiskey and what was this guy's name? Davido, or maybe Michael Jackson should just show up for a conference that you don't want to attend. Then all of a sudden, under 11 minutes, the whole stuff was sold out. So this is just like reminding me of back then when we were in school. So normally there's this what we call hostel ballots. I don't know, I may not remember hostel ballots. They will tell you that you should wake up by 12 a.m. That by 12 a.m. that when you bring out your scratch card, that somehow you get hostel. It's a lie. So like I all through my 5 years in that school, I never got hostel. So but somehow I get hostel at the end of the day. So I don't score. So somehow, so to cut the story short, this gets to tell you that a lot of stuff is happening and people are really taking AI serious. If they can sell this conference out under 11 minutes, man, they are made somehow. So to cut the story short, I want to talk about how what has happened last week influenced why you guys should take AI serious. So first of all, so why you guys should take AI serious? Because first of all, this guy said something. Okay, let me leave this guy. This guy said something. He said, "Wow, coming from Africa, where the internet takes about 11 minutes to get to the payment page, I seriously feel depressed. How are we supposed to even have a chance? Seriously, how are you guys supposed to have a chance whereby you know that your data, even today, we are struggling with data. Like, it's a very big problem. And this is not just a big problem. This gets to tell you that your structure, the infrastructure is kind of, it's not good. You have poor infrastructure. And when you have poor infrastructure, you can't compete. Let's be realistic. You can't compete with the best in the world. You can't. You don't even have good power supply. You can't. But I'm not trying to make you feel depressed. No, that's not the point. Relax. I'm not trying to make you feel depressed, but what I'm just trying to let you know that if you are going to compete, you have to like step up your game. Like you don't have to wait for the government to step up your game for you. You have to step up your game yourself. That is what I'm trying to let you know. So you have to like put in extra work because why these guys are building this AI product, they are building it with respect to their environment. And if they keep building this stuff with respect to the environment, that means you guys are being excluded. When you use the product does not really give a fuck about
We
it.
are being excluded. We, not you guys.
No, we. Yeah. So, Wretched,
Radiant.
how do you pronounce this name, Jeff?
Radiant.
Radia Baby. So, well, this is my AI crush, you know. She has this nice
And she's
afro.
joining us very soon.
By the way,
You can
when she joins us, just let me know. So I want to talk to her personally. So, she's the co-founder of Black in AI. So, what Black in AI is trying to do is to create awareness in the AI community by bringing Black people together to take AI serious, and also they tend to like bring Black researchers all over. You want to bring.
I want to talk about Black in AI.
She wants to talk about. I think she's a rep, so she will talk about Black in AI.
So Black in AI is a very huge community which all of you should join. It's more. Sorry. I said Black in AI. Do you have internet? Let's Google Black in AI. So I said Black in AI is a huge community. Do I have to stand? So what I was saying in essence is that I just want to talk about Black in AI. It's a very big community doing a lot of work. It's trying to make the problem of diversity in terms of getting more Black people into the room where the decision is being made. Imagine going to a conference like NIPS and all you can find apart from yourself is one other Black guy in a room of white guys. We are talking about cutting edge research being done. We are talking about AI that we intend to make available for the rest of the world. And the people that are making the decisions, that are doing the top-notch research, are just out there that looks nothing like you, and they're trying to propose solutions to your problem. Have no clue from where they are. So Black in AI they bring about more researchers from Africans, like not that whites are not also part of Black in AI, but there's always that exception. You go to women in machine learning meetups and you still see guys, you understand, it won't take you nothing. But the thing is that we want, but it should be more of the Black community coming together, and Black in AI is where you can find, maybe you're looking for a job. I get a notification almost all the time. People saying things like, we have an opening here in blah blah blah. We are looking for a researcher in blah blah blah. Do you understand? So you can promote your work on Black in AI on Black in AI page. There's a Facebook page. On Twitter, you can always follow Black in AI. On Google, there's a Google. What's it called again? Google Plus. Now that's what I use more because I found out that I don't like to check Facebook all the time. So for Google Plus, I get an email anytime someone asks a question. And for these NIPS, before it even started, as it was starting, you see a notification that guys register for NIPS. It's just going to be open for a couple of minutes. And even when people registered for it, they were still asking, okay, so here's the story. Sometimes for NIPS, some people even register for more than maybe it's like a celebrity show or something. So one person could have bought maybe like 10 tickets. One person. So you might want to sell your ticket eventually, or maybe you thought you were going to go and you didn't go. So community like Black in AI would ask you to fill a form if you want to, if you don't think you would make this and ready register, so you can transfer your ticket to someone else. Do you understand? So if you want to go to Black in AI, there's a Black in AI conference as well. So the Black in AI conference happens with NIPS. So it's a one-day conference that happens during NIPS. So if you get a scholar, a grant to go to Black in AI conference, that doesn't necessarily mean that you can attend NIPS. Do you understand? You need to register, but it does not make sense for you to just go for one day and not attend the whole of NIPS. So you need to register for NIPS to be able to do that. So all I'm saying in essence is that you can gather all this information on the internet just to get our feet wet. So please join Black in AI community. It's a lot of good for you, a lot of information we can give you from top, and you can talk to top-notch researchers. You can just buzz them like they are just there. Like Mustafa Sisse, who is the new who heads Facebook, or the new Google research lab in Ghana, is Black in AI member. I mean, literally, you can just say, I have a question. Everyone will see it. I mean, you want to ask a question, you need an answer. Somebody will answer you. There is no discrimination, and that's how you get. Sometimes that's how you get results for what you want. You need to be bold enough to ask the right question to the right people, and they can help you. And one last thing, like what Jeff Dean said in his talk. I was not there. He said something like yesterday at Inga, but it was more like the way you grow quickly is by talking to people that are high ahead of you in terms of what you're trying to solve a problem. But like an expert, you understand, you need to grow into the community where they're actually where they're doing what you want to do. That is how you can quickly move ahead. So if you join community like that, that is how you can move ahead in this field. If you really want to be in this field. Women especially is very, very important. Like Timnit Gabriel is one of my mentors. She's just going to hold me on my neck saying that, where are the women? Women have to join the community. Like, we want more women. Like, it's fantastic that guys are here, but we want more women in the community. And she also said something. She said every single guy that comes for AI Saturday should bring a female friend to class.
You don't have.
And then she joined us for the first week of AI Saturday. She joined us for intermediate class, and maybe some of you have gone, or maybe some of you were not here. So she was like, every single guy that comes to class, to this class, should bring a female friend along next time they are coming. So that is how serious it is, and it's very important to encourage our female friends and like junior ones to come to go into this field and all. So
Thank you.
You're welcome.
All right, thank you very much. So, another thing you can do is, if you really want to register your son, just like what this guy said, I'm thinking about getting my son registered for NIPS for 2014. Once I get the confirmation, I'll start searching for the wife. So, I'll start searching for the wife. First of all, I have the money. This is Dota 2 competition, current AI competition, and we played against human. So what this stuff does is, with the help of neural network, it takes in game data, use it to predict the next move. The same stuff happening here with coordinates. It takes in image, use it for object classification. So basically, this box is just neural network. With neural network, you get better representation. So, with neural network, you can approximate any function. So back to the matter. As humans, we learn, we recognize patterns, we solve problems, we create stuff because of our brain. And this is for human. Tolani, what was her name? Tola, you're making noise. Yeah, so as human, we can learn, we can recognize patterns, we can do all this stuff because we have our brain. So our brain, I don't want to say what let me just close my mouth. So with our brain, we can do a lot of stuff. So, and why? Probably God created us with something powerful that other organisms, they don't have, or probably because of science will tell you because of evolution. So let's leave that talk aside. So the brain is a very powerful tool that is enabling us to solve a lot of problems. So with computer, you have what we call neural network. Neural network will enable them to learn, recognize patterns, solve problems, and create new stuff. So let's go back to Andrew Ng's course. How many of you watched the video? I want to see your hand. Don't be shy. So the prerequisite of this course,
Is to watch video
of
before
coming to this class, is to watch the video before you come to this class. Like, if you, okay, I don't want to sound arrogant, but if you don't watch the video, you won't understand what's happening. And if you don't understand what is happening, it's bad. It's really bad because you just showed up and you don't understand what's happening. So it's very important you understand what's happening by watching the video. And my point is, watch the video. That's like my point. Don't just show up, just watch the video. Like, you can't come to this class and occupy space and you don't watch the video. So just watch the video and eat our food. So back to the matter. I'm sorry. So back to the matter. So we have what we call a semantic gap. So when computer, when they see pictures, when they see images, let's say this is 28 by 28 pixel. Let's say you have circle in front of it. We have, this is O, or we have O or circle. So this is how you see. This is how you see images. This is how I see you. I see you as normal picture. Let's say we have like so how computer will see you is quite different. What computer sees is 0 to 5. So 0 stands for what? Why 255 stands for what? All these web developers, this is where your thought ends for you. So so I'm sorry. So at least your skill is transferable. You can see, you can use it, mixing. So my point being that we have what we call RGB channels. So what computer sees, it sees in your R channel, it sees 0 to 255. This ranges from 0 to 255. In between, you have your black, white, violet, different colors in between. So by the combination of these 3 color channels, you can generate any color. So for computer, what computer sees is just 0, 1, 4, 9, all this stuff. That's what computer sees. As human, we see real pictures. So I don't know. Just imagine that you are a computer. How are you supposed to like make sense with real picture? It's difficult. I don't know whether you understand my point. It's really difficult. So this is what we call the semantic gap. The ability for you to like make sense with these numbers. To know that this number represents car. This number represents Femi, Bayo, or Teju. So then with that, what we have been doing lately, we have with that you have like your car. Then you want to like classify car. You have like your car. You get your car images. You get some stuff that don't look like car, like bike, like shark, like tree, different stuff. You use it. You use this data to you run it through your model to train your model. Then you can use it to classify your car. So my point being that if you are going to do classification, let's say if you want to represent this car in a graph, let's say you are going to take these 2 positions, you are going to take this part and this part. You want to represent, you want to like grab them, and you want to grab them in such a way that you have your car and you have your non-car. So here we have your non-car, here you have car. So from here you can see that you have car clustered in this region, then you have your non-car clustered in this region, just for 2 pixels. For these 2 pixels. So my point being that with your linear classifier, you know what you can do with your linear classifier? What can you do? You can draw a straight line. Can you draw a straight line here? No. Why? It won't be accurate. So this is why you need neural network, because neural network can map any function. We call it universal function approximation. It can approximate any function. So you bring in, neural network can bring in non-linearity. Because in this situation, you don't need linear classifier, you need non-linear classifier. Does it make any sense? So let me just so normally you have let's say you have x, then you have one, oh yeah, you have one x, you have o. So if you should draw a straight line here, your model won't generalize very well. So you need something that can fit. Probably do something like this. You get. So this is non-linear model. Make sense? Yeah. So back to the matter. We have in this situation we have a pixel of 50 by 50. We have 50 by 50, and this 50 by 50 is equivalent to 50 times 50, 2,500 pixel. Then, how many color channels do you have? 3, right?
Yeah.
So times 3. Right? Let me not use pixel. RGB. So yeah, that's pixel. You have this. So my point being that you have multiple pictures. This is not just pixel 1 versus pixel 2. If you have in this situation now, we have about what? We have about 2,500. You have about 7,500 if you're dealing with RGB. If you're dealing with grayscale, you just have like 2,500. So point being that we have multiple pictures and we want to make sense with these multiple pictures. We can't use linear classifiers. We can't even use logistic classifiers. We have to use something big. That is neural network. So that is what is happening here. And if you want to use algorithm like support vector machine, they're fine, they will work, but they won't work very well. And the computational resources you need to train this algorithm is quite much, and also they tend to like overfit, and you don't want that. So the point there is that you need something. You have to it's like bringing in your bazooka or bringing in your rocket for serious thing. You can't be bringing in bicycle for. If you want to go to the moon, you can't be driving bicycle. So you have to bring in something reasonable. And neural network is like that thing that you have to bring in when everything fails. So I think I've explained this stuff. So basically, SVM, they can learn very well, provided you give them the right representation of X. The point being that this is just your voice. This is how we communicate. So when we take in voice, you have to like process this stuff. I think either Fourier transform or Z transform. After doing this Z transform, you feed this representation to your SVM model, XVM algorithm. When you feed this model, this stuff to your SVM algorithm, it makes sense with it. You use your representation. But you can't feed this guy in direct, it will not make any sense with it. So with neural network, you can feed this guy straight up, your raw data straight up, then it will make sense with it. Get my point? The same thing with this. On a normal day, if you want to use SVM to classify fruits, you want to use it to identify an apple, you're supposed to break it down to 3 color channels. You know that we have red. Red is dominant in apple. So by separating it along these 3 color channels, so you know that you're going to pick probably you feed these 3 color channels in, then this red is dominant. It that red is what is should I stop it? It is that green will have more stuff happening in your green color channel. That means you have green is dominant there. So that means that one is for Kumba. you have another thing, probably, and what's yellow, probably orange, banana is yellow. So you know something else is quite dominant there. Using this histogram, this color histogram. So my point there is that if you're going to use neural network, you don't necessarily have the raw image, you run it through your neural network, then it does classification.
So this is what is called feature extraction.
This is what you call feature extraction, this is what you call feature extraction. So you have to extract the feature, then pick that feature being extracted, you run it through your model. But for neural network, you don't do that. You just take your raw image.
Basically, SVM needs feature extraction, which is a tedious work. It means you have to add code almost everything. For instance, if you want to code for this apple, you would say that if you see something that has something on top, that has anything that works for this apple, if you had coded that the stick, what's that on top? The stem, rather, right? It's a branch or something. If you had coded it down, if you see this and this and this, then it's an apple. If you give it an apple that does not have it, it's not going to recognize it and have it. You have to put much more of those features for it to recognize. For neural network learn representation, so you add code, you have to engineer feature for this to make SVM work. But for neural network, you don't need to do that. You just learn the representation itself.
Makes sense, right?
Like it's crazy.
Yeah.
It's not just making sense. It's crazy.
Thank you. So back to the matter. You have for humans, the way we learn, we don't do feature extraction when we learn. We learn based on raw inputs. Like I know you're human. I'm not going to say that you have. We don't do feature extraction. We learn based on raw inputs. So the same thing with neural network. Let me talk about neurons. Just bear with my drawing. So this is what we call your dendrites. This is what you call your cell body. This is what you call the myelin sheath. This is what you call axon, right? Okay, that stuff is missing. Synapses. Let's just say synapses. So this is cell. This is not the one we do in biology, but it's close to it. So this is your neuron. All together, this is your neuron. So this is the fundamental building block of your brain. So this is how it works. You have what do you call them? You have neurotransmitters. These are chemicals. These are chemicals. I don't know whether it's hormone or I can't remember. But basically, they are just chemicals that interact with the cell body. So when they interact with, first of all, they interact with the dendrite, then the dendrite will interact with the cell body. Then, by doing this is a chemical reaction. This is a chemical process. Then this is electrical process. So what actually happens is that they interact with the dendrites, then the dendrites will interact with the cell body. This cell body acts as a threshold, what we call thresholding. So it acts as a threshold based on how much the chemical, the neurotransmitter is, based on how they interact with the cell body, with the dendrite. So this cell body act like a threshold. It's going to be the one that will say, okay, let's assume that the neurotransmitter, they did a good job. It's going to be like, okay, fine, you guys did a good job. I'm going to transmit this information. I'm going to transmit this electrical signal. If they did not interact very well with it, it's going to be like, well, I don't think I'm not going to transmit anything. So what actually happens here is a chemical process. What actually happens here is the electrical process. So it's going to send, the cell body is going to send electrical signal along your axon to other cell, to other dendrites that are connected to other cell bodies. Does it make any sense? So what's happening here is chemical process interacting with this this dendrite. Then you have electrical process that's also interacting with other cell bodies. Make sense? Fine. So that's it. So this thresholding part, we'll get to know about this thresholding part in the future, but let me just talk about it. So this thresholding part, you guys did logistic regression, right? So
0.5%.
I'm not asking for the 0.5. What is it doing? What's happening here?
So the threshold is being set in order to be able to know when you have a positive class and when you have a negative class. So it's a boundary.
So anyone from the back, what's this cell? What's this stuff? What's it doing?
When you get there, you have to know above.
The output is above all. So basically, it's act as a thresholding. What's happening here? So we call it activation function. You have your signal, you have your RELU, you have your TANH, then you have other activation function. So what this one does, this one is a signal function. What it does is that if the signal, if the chemical interaction in the dendrite is not sufficient, don't send electrical, it's not good enough, don't transmit electrical signal. If it's good enough, if it's something reasonable, something worth transmitting, activate, send electrical signal. Doesn't make any sense. So it acts as a gate. If you are good enough, lets you in. If you are not good enough, man, it sends you back, or it doesn't even care about it. So that is what this guy does here. Makes sense? So I think we have talked about this. So here, what's happening here? This dendrite is like your input. Your axon is what? Right? So we have input coming through the dendrites into the soma, which is also called the cell body. Then the signal goes by the axon to other neurons. Then this is just neural network and other stories. So, I think we talked about thresholding. We talked about your inputs can be numerical vector. Your inputs can be numerical scalar or vector. It can actually be anything. We'll get to talk about this one later. So when it comes to the brain is a universal learning algorithm. Just like neural network is universal function approximator, your brain is a universal learning algorithm. Your brain can learn anything, like on the go. So let me just give you the instance of what actually happened. There's what we call the auditory cortex. This is the guy that's in charge of how you process how you process audio signal. So what they actually did was that they disconnected, they cut the ear off, and they connected the visual, the eyes to that part. What they later discovered that the auditory cortex could also, by disconnecting the ear and connecting the eye, the auditory cortex could now adjust itself, could now learn how to process visual signal from processing auditory signal to now visual signal. So what does this tell you? It tells you that the brain is learning, knows how to adapt. So the same thing happens to neural network. You need something like that. You need something that can adapt to different inputs, irrespective of how your signal is, whether it's visual, whether it's audio, irrespective of how it is. So the same thing happened here too. They disconnected this guy, your somatosensory cortex, then they plugged in the visual. The same thing happened. So you have one learning algorithm hypothesis. So the point there is that you need something like the brain that can adapt very well with your signal. So here we have, I think I've discussed this. This is your input, this is your input, your dendrites, your output, your axon, then you have your myelin sheath and connected to other neuron. So now is the part that most of you will sleep. Do you have any question? Let's just pause it for any question.
So the cell body is it acting what is cause control?
Cell body. This is the cell body. We have not discussed about this is the cell body. It's acting as what is here. It's a mixture of two things. We'll talk about that. It's a mixture of two things. We'll talk about that. So any other question? You guys ask question, please. Yeah, you can use neural network to predict consciousness. So there's a branch of not really, there's an architecture of neural network you can use. We call them recurrent neural network. And under recurrent neural network, we have what we call LSTM, which stands for long short-term memory. We have another one called GRU, which stands for gated recurrent unit. So you can use any of these stuff. So they are very good with sequence-to-sequence problem, like text, video, and other stuff. So you can use it for time series problem. Any other question? Yes.
It's going to someone that's the input, but the output.
What input?
The input.
Yeah. Okay, this is what it. I think we have what we call neurons that neurons that fire together wired together. Hope I did not flip this stuff. If it's not neuron that wire together and fire together. I think this is it. So point being that how is this topic related to what I'm about to say? So point being that the fact that these guys are all together, if the signal generated, if it is that strong, it's going to fire. If it is not strong, it will fire. So it will not fire, meaning that the threshold, the guy responsible, that is the activation function, will not switch. Like your sigmoid function, you switch from 0 to 1. So it's not going to switch from 0 to something reasonable, greater than 0.1, 0.5. So it's not going to switch. It's going to just die there. It's not going to pass any electrical signal. But if it's something meaningful, it's going to fire, and then it can propagate that order. Any other question?
If your data is not so much, it's not large. What is does it have any
One of the main criteria of using neural networks is data. You have to have sufficient data to train your model.
That's how sufficient.
Yeah, and okay.
When do you know when to say, let's just apply that?
Yeah, to be honest with you, you have to The data has to be merged. It has to be merged. But sometimes, like lately, people don't really use much data. But if you have computational resources, you still have to like train. Like Facebook, when they don't train like small data. They have the data is not their problem. So they train massively. Same thing applies to them. We have sufficient data. They train. That's why they say data is the new oil because having data, you have leverage. I can't just wake up, but that doesn't mean that a normal startup can go into the field. Yeah, that doesn't mean that. It means that you're going to go into a very niche field whereby you guys are not really interested. Then you make yourself relevant, or you can just as well as optimize what they have been doing. So my point being that you really need that amount of data. But sometimes you don't necessarily have to use. You can use pre-trained model. I don't know where I've heard about pre-trained model. These are data. These are models that have already been trained on.
Maybe on different models.
Maybe Google must have trained with their image, with the all images. Then they have like a pre-trained model. Then you download that pre-trained model. You now use your own data to retrain some parts of the pre-trained model. Because that pre-trained model, they have like a knowledge of how they have better way of recognizing features because they have been trained. So it's more or less like we call that part transfer learning. So they are transferring the knowledge then to a new program. So, but you have to be very careful with how you do that because some pre-trained model are quite biased. Like some pre-trained model, all it now to do is to recognize stuff. So quite biased. You have to be very careful with that.
So in terms of function, I think the only thing I show I think other functions are critical.
You have Relu, you have Tankish, then you have Sigmund. Then you have you have different brands of Relu. You have your liquid Relu. Then you have so many
depending on the class of problem.
yeah, it varies. But currently now they use Relu for a lot of problems because of what we call vanishing gradients. We'll get to know that by next we'll get to know about that. We also use standards, depending on the kind of problem that we do. But most neural networks they use Relu a lot, and sometimes they use liquid Relu. Why they use sigmoid function output? Yeah, that's what you use your sigma. So let's just. So, so far so good. When it comes to linear, regression, this is how we have been representing our hypothesis. Right. This is how we represent our hypothesis. We are going to logistic regression. How do we represent our hypothesis in logistic regression? You guys did logistic regression. Huh? Sigma. I'm talking about this. What's this guy? Okay. 1 over what?
1 plus.
Is it minus or plus?
Okay, 1 minus.
Minus. Okay. So I can represent this stuff. Which other way can I represent this stuff? Which other way can I represent it? Where where this guy is what? Let's assume that this guy is his whole part is C. Right?
Yeah.
So let's do our this is our cell wall, our cell body. Then we have our just bear with me. So this is then right, this is your cell wall, cell body. This is your axon. Stuff to something reasonable. Let's just do the math part. So we can also represent this stuff as this summation. We are so this is our X, this is our input. Your dendrite will receive your input. This is your input. This is your what? Output. So these connections here, with respect to neural, with respect to linear regression, we have this, right? What's our weight in linear regression? What's our weight? Theta not and what? What does it create? No. What's the mean interpretation? What's the bias and what? And the gradient.
Intercept.
Yeah. Bias and intercept slash bias and slope of gradient. So we have M and G. So when it comes to neural network, you have your dendrite, and based on how your dendrite is connected to your body, based on this connection here, based on the kind of weight you have between your dendrite and your cell body, you have, this is where your theta comes in. I don't know whether it's making sense. Based on this weight, maybe this weight is strong, maybe the connection is strong. You have your theta, this is, you have your theta here. Let me just say this is theta 1, then you have theta 2, theta 3, theta 4. So based on the relationship between your dendrite and your cell body, this is the length weight, this is what you are going to learn at the end of the day. You're supposed to like learn this weight when you based on how your model will interact. After training your model, this is what the weight you're supposed to learn. You're supposed to know that, oh, if I should see eyes, if I should see line, that this means that if I should see eye plus mouth plus every other stuff, this is supposed to give me this. So this is what you're going to learn. I want to neural net so you understand this weight. In this situation, you're not going to be having your P and M. You're going to have like normal. You have to have relate that to what we have here. So we are going to feed your input. Let's say this one to x1, x2, x3, x4. Just as is an assumption. So this is your neuron in the brain. This is your representation of your neuron in terms of logistic. This is a logistic neuron model in terms of computer style. So here you have your input. Then you feed your input to your whole body. Then it thresholds it. It makes sense. It sends the electrical signal. From there you will have like your hypothesis model. We are just trying to like create like hypothesis model. I don't know whether you remember. So we have discussed the one for linear integration, we have discussed the one for logistic integration. This is what neural network has to do. So basically, when it comes to neural network, we use logistic units is a building block of neural network. So each unit of the neural network is a logistic unit. Stack them together. You have multiple layer perceptron. This is a perceptron. When you stack them together, you have multiple layer perceptron. With this multiple layer perceptron, you can solve a lot of problems. That's what I'm just trying to say. So this is it again. So you have your input layer, you have logistic units. Each of these stands for logistic units. You bring them together. All together, you have this just like your model, your hypothesis representation with respect to neural network. So you have your hidden layer. You don't necessarily know anything that is happening here. So your hidden layer is you can't observe what's happening in it. It's not observable. You don't really know what's happening in the hidden layer. But sometimes what we do in cognitive is that sometimes we slice the hidden layer to know how maybe this neuron is responsible for seeing line. Some might be responsible for seeing mouth. Some might be responsible for seeing. So when you bring everything together, this one's supposed to be responsible for seeing face. It makes sense. So that is what is actually happening. So you have your input layer, you have your hidden layer, then you have your output layer. So I want to say something about deep learning, about deep neural network. So it's quite controversial because some people have been saying that for you to have a deep layer, you have to have like 5 layers, you have to have like 4 layers. So they wanted to do what I to have like a deep layer, you just have to have like a one hidden layer. Once your hidden layer exceeds 1, it's a deep neural network. Anybody that would argue, just the person to argue with itself. So, well, that is what it is. That is the standard convention. So, it's quite controversial, but some people still need that to like start of this layer to have like different layers, many layers or multiple perception for you to qualitative neural network. But based on what I think, you also have to have like more than 1 layer. You are good to go. So, there's definitely ignorance, but we'll come back to this part. So let's just do this stuff. It's like the only mathematics we are going to do today. So any questions so far? Has not been what? I didn't hear. You have not. Okay, we are there. The neuron is responsible for. There's something wrong with you, something, you know. The fact that your sensor is not working well, is it your sensor that is not working well? No. Your sensor is, I don't know, let's make sense with it. This is down to, then you have your, this is your hand. Then you have your brain. So pardon me. Let me just draw this hand for you. Looking like just like that. It's close, this cartoon, so let's come back. So we have your hand here, you have your candle here, and what parts are you having issues? Let's know. Your hand. Your hand is not transmitting enough signal. So that means there's something wrong with your sense, your hand. Yeah, there's something wrong. So since there's something with your hand, that means your primary store in your hand is to send signal to your brain. That's what it is. So,
how can you correct that?
George, I think I can answer that.
okay, wants to answer the question, please.
So if you relate it to how now the whole idea is you have your inputs, then you have your hidden layer, then you get an output. Now the output is coming from your brain, that's your reaction to it. So if in this case you move your hand close, you're not getting any reaction. That means it's not passing enough signal. What do? You readjust the weight. And how do you readjust the weight in real life? Keep moving your hand. So once you get a reaction, you've been activated.
Let's assume that your sensor is
Before
working
you
very
get
well.
the reaction.
But you just want signal. You want to activate that.
What's the one in this case? That's the correct way to activate
I
your
think
senses.
it makes sense, yeah. I like that. Makes sense. But let's just do this guy here. So this is what? These are our what? Hello? This is what? Then this is what? Then this is what? Let's see, this is our x1, x2, x3, right? So then we're supposed to, I don't want to, this is how it works. You're supposed to like connect, this X1 is supposed to be connected to your hidden layer, each and every one of the hidden units of your hidden layer. Then this one too is supposed to connect to each and every one of them. This is how it is. But I don't want to clutter the diagram, so you're going to take it part by part. In neural network, we have bias. Please don't forget that we have bias, and we're going to bring in the bias. We'll bring in the bias, just like in linear regression, just like in logistic regression. You have your bias. So let's just bring in the bias. Let's just put it somewhere so we can see it. So this is your bias. And now, how do you denote bias? So I'm not happy with this. So let's start with this one. This is your A2, 1.
Yeah.
You know why we call it A2? Second layer. That's where you have 2. Your 1 there stands for the units, the first unit of your second layer. So let's connect. Right? So what are we using? Wait, what are we using? Let's just put theta. So here we have theta 1, 0, theta 1, 1, 2, 1, 3, right? So let's call this let me just we know that this is theta transpose x plus theta 0 x 0. Oh, it's making sense. This stuff makes sense. This is our bias. Is it making sense? Yes or no? This is what our hypothesis. With respect to logistic regression, we have your sigma. It's inside. It's outside. It's not outside. It's still outside. I was thinking about the position. So let me just take it. So let me keep the position. So you have sigmoid function here. So let's call this guy all together, all of them, they are z. You have theta z. Does it make any sense? So now we want to get z for this guy. All together we have our a. So we keep changing these values. Let's call this I, subscript I1, this is I2, this is I3. Make sense? Yeah. So now we want to get z of A1. Does it make any sense? So we want to do that. So let's do that. So sigmoid function outside. Then let's bring all our theta. So we have theta 1, 0, x 0 plus what? 1, 1. We have a sigmoid function. Right. So I'm going to erase this connection, but you can connect it to your group. So we have gotten this guy. So let's do one. A 2 2. So what's going to be our weight? What's going to be our weight? Our weight. The 2 what? And the second what? 2, 1. Is it making sense? Is that this guy? Is it making sense? Yeah. So we have our sigmoid function. So what are we going to do? Start what? So then plus theta 2 1 what?
X1
Plus
theta 2 2 x2 plus theta 2 3 x3.
this is what?
A2 2.
Makes sense? So now let's do this guy. A what? So you have theta what? 3 0 3-1. Right? Right? All together you have what? A. We have this connection. Let me just clean this guy. Let's just reconnect. Let's just bring them back to life. Understand this part, right? So, I'm going to erase this part. So you have done this whole part. What's missing here? What's missing here? A0. A0 what? All this stuff is making sense. That's like the most important thing. If it's not making sense, you can just stop and start. Not really start over. So, what are we going to call this guy? A what? A3 what? A3 what? How many neurons? One. How many neurons do you have here? One. So the 3 stands for the layer, the 1 stands for the neuron, the position of the neuron. So now, this is our bias, so we are going to connect it. Right? So let's do that. So what's our weight going to be like? What's our weight going to be like? It's going to be A1. Makes sense? So let's just do it. You have what? Starting from the theta 1, 0. Then what? Plus plus
No, 8 weeks of 3 down. 2, 4. Yeah, 2 years. Down 2.
then your sigmoid function. Then what do you have? Then this guy is this guy here, right?
Yeah.
If you apply sigmoid function to it, you get your hypothesis. So you all know what actually happened here, right? So you can do this at top, right? Yeah. Okay, so let's talk about what's the time? 12. So what's the importance of your activation function? what's the work of the activation function? What is the work of your activation function? What's the work of this guy? This G. What's the work of? What do they do? It brings in non-linearity. That's like that thing that is doing that thing. That's what we call non-linearity. So it brings in non-linearity, and when you bring in non-linearity, it enables you to map complex functions. Without that, without those activation functions, you still have your normal linear classifier. So when you take this activation function, you still have your normal linear classifier, you still have your straight line. But by bringing activation function in, it introduces non-linearity. And with non-linearity, you can map complex functions. So let's talk about XO problem. So before we talk about XO problem, we're going to talk about AND, or we're going to talk about Boolean gate. So let me just describe the XO problem, then from there we'll talk about Boolean gate. So this marker is so how are you going to draw a linear class? What kind of, how are you supposed to, what if you should apply linear classifier to this, what will happen? Is it going to generalize your, let's say we have like a linear classifier. You are going to separate this guy from, so you still have like element of this guy here, so it doesn't generalize well. You should have another one like this. You still have this guy here, it doesn't generalize well. If you have another one like this, you still have this guy here. You still have this guy here, it doesn't generalize well. If you have another one like we have done this, you have another one like this. You still have this guy here, it doesn't generalize well. So you need something that will separate this guy. You understand? So with one neuron, with one perceptron, you can't solve this problem with one perceptron. You can't. One perceptron can. One perceptron can do this, but one perceptron can't do this. For you to solve this problem, you have to have minimum of 2 perceptrons to solve this problem. So this is the classical XOR problem. So you understand what XOR problem is. So now let's talk about let's talk about Boolean gate. So we have different Boolean gates. How many of us are familiar with the truth table? So we all did mathematics in school. Sorry, we all did mathematics. We all did further maths in school. I'm sorry for assuming so. Let me talk about the truth table. Let's talk about the and truth table. So you have let's say you have 0, we have 1. You have 1, 0, 0. Okay, let's use them. 0, 0, 0, 1, 1, 0, 1, 1. So for the AND gate, two elements must be the same for you to get. How am I supposed to describe this stuff? You will see like, when I these two they are the same. To give you 0. This one will give you what? This one will give you what? This one will give you what? So this one should explain this. This one is what? Thank you. True, when what? When both are the same.
So when both
When
are
both are true. Okay, not when both are
by
the same.
condition is that 1 is true and 0 is false.
False.
So it's true statement.
See, this one they went to good school. So you understand what it is. If you don't understand, you can simplify because this stuff is going to mess with you in the future. So does it make any sense? Fine. So with one perceptron, you can get this AND gate. This is your hypothesis. So how does it work? Let's say you have this is your bias plus 1. This is your x1, x2. Then your weight. You have 13. You have plus 20. You have plus 20. Let's make sense with this stuff. From what we know that our hypothesis is B plus summation I theta what transpose x, right?
Yeah.
What's our B? What's our B?
Plus 1 minus 13.
So we have let's leave the G out. Let's just say B is what?
Minus 13.
Plus 1. What's the weight?
Minus 13.
Minus 30 times plus 1.
Minus 13.
What's the next one?
It was 20x1.
We want to say anytime this thing.
I'm not sure that I'm not sure.
What happened to the plus 1?
That was one.
No, the
No,
bias
no.
term is plus 1
The
and
bias
has a
term
weight
is
of
1.
minus 13.
Is plus 1. It has a weight of 30.
Theta 0, you know there's theta
This
0,
part
theta
is-
1.
Yeah, this is your theta. This is your x0.
X0.
This is your x0.
So it's actually the bias
Yeah.
Yeah.
I don't understand what
Actually,
is
now I understand what he's
What's
saying. You know, the formula is theta 0 plus x1 theta 1, and theta 0 is the bias.
your theta 0.
Yes. So when calling plus 1, theta 0 itself is the bias.
That's why I started from 1. I didn't start from 0.
No, you don't get. You
I
said
don't. This
theta.
is what I started from.
You said theta 0. You said bias is plus 1, and it has a weight of minus 13. It's kind of like a counterintuitive. Like the theta 0 itself, the weight itself is the bias.
Okay, sorry. This is what you want, right? This is what you want now,
No,
right?
it's on. I think we understand.
Okay, let me make it look like what we have here. Let me make it look like what we have here. We have
Do you understand?
x naught
Theta 0 is
theta 0. I started from 1. I skipped that one. But that one outside, this x naught and x0 stands for the bias. Does it make any sense?
Actually, theta 0 stands for bias. X naught is just to make the mathematics simple.
So it's simple, yeah, theta
So
0.
so it has nothing to
Okay, I
do
get what
with
you're
the
saying
bias.
now.
So
Okay,
that
I
is
get
what
what
it's
okay,
saying.
that's what you're saying. So your theta 0 stands for
The bias.
bias. Your
Yeah.
x1 stands for
X naught is just
1, just to make it
Just-
mathematical convenience. Thank you. So they don't know what it is, so they just say it's mathematical convenience. So you should multiply. We have done this. So let's do for this one. X1 times 20. What are you going to get?
20x1
The next one is going to be what?
plus 20x2.
So let's bring in our, this stuff. Two things actually happen here. We have your summation, then you have your activation. Your summation, your activation when you put G. Make sense? So from there, let's apply this stuff. Put 0 for x1 and 0 for x2.
That will be minus 30.
So that was going to be minus 30.
Minus 30.
Let's just put 0, 0. What are you going to get?
G of minus 30.
So you have,
Minus 30G.
right?
G of minus 30. Yeah, no,
Yeah.
yeah.
You have g of minus 30. If you run it through sigmoid function, what are you going to get?
I mean, they said
What,
approximately
what,
0.
what was the region?
Let's do that be
This-
1 over 1 plus exponential minus 30.
So
Exponential minus 30
it's
is
not going to,
okay, yeah,
it's
exponential
going to be in
30.
this region. It's not going to be in the positive region.
Ah, exactly.
So if you want to do it, you can calculate it. Feel free. You're going to be in this region. So you're not going to fire. You're going to, even if you are going to fire, your output is going to be less than 0.
Yeah, 1 over anything that big will be
So,
almost 0.
0. So it's going to be close to 0 or almost 0. So it's not going to flag. So if you should put, let's put 0, 1. We have 0 here already. Let's put 1 here. So what are we going to have? We're going to have minus 30. What are you going to have here? So what are we going to have at the end of the day? So what will happen to minus 30? You should run it through that function. What are you going to get? You're going to get 0 too. We should run, let's do the second one. We should, since both of them are the same thing, we should flip the position, still going to get minus 10. So we are going to get another 0. So let's do 1, 1. So for 1, 1, you're going to get 1, 1. 20 plus 20. Minus 30. 10. So you have G10. This will give you 1. So this is your AND gate. Does it make any sense? I hope it makes sense. Is that your... I'm not going to go through this stuff, but I think you guys should do it. If you want to do it. This space is not sufficient for me to
Why do we need X now?
Why do we
Intuitive.
Yeah, the reason is because
I'm tired of the math. Why?
with this stuff, with this XOR,
Yeah.
this XOR problem, if you should normally all we have been working so far is just one single perceptron. You just have just one single perceptron. So let's assume that one single perceptron is going to solve your AND problem. Another perceptron is going to solve this problem. Another one will solve your OR problem. If they combine them together, you are going to create, with respect to geometry, you are going to create like an hyperplane that will
Okay.
give you a function. that will divide. This is like a decision boundary.
It's like not explicitly doing this zero, what's it called, this classifier for logistic regression, all for all or something like that. One versus all. One for all. It's like, so I'm asking you, Josh, is it like that? It's like doing one for all, but combining it in a way we can't see.
So basically, this is one perception. One perception can do each and every one of these stuff individually, but it cannot
combine them together.
You cannot use it to solve this problem. But when you stack more than one perceptron together, stack them, you have a multiple layer perceptron. You can use it to solve XOR problem. It's not just XOR problem, you can use it to solve different type of problem. So the essence of going through all these basics is for you to have like an intuition of what the limitation of perceptron. And by knowing the limitation of perceptron, you know that for you to solve complex problem, you stack them up. And by stacking them up, that is where your neural network comes in. Does it make any sense?
And then we can go deeper.
Then you guys can go deeper. But this one you do it at home. You're not going to do it here. So, no, you're not doing that's why you have to watch the video. It's not simple. So it's not I've done the basic part now. To be honest with you, I've done the basic part. So we did something like this now, right? Yeah, you have done the basic part. When you stack them together, you get it. So go and do it at home. So when you do that, okay. When you do that, let me discuss this guy. So when you observe, let's assume that I don't know. You guys should look at this part. Look at this part. This is your first hypothesis. This is your first unit of your hidden layer. This is your second unit of your hidden layer. Let's assume that this first unit of your hidden layer represents this hypothesis. This one represents another hypothesis. While your output layer represents your third hypothesis. Hello, can you hear me? Yeah. So now, this hypothesis here, this one here, by observing the input, by observing the input, you have 0, 0. This one represents x1, x2, x1, x2. So by observing the input, what kind of gate is this?
This one is all gates.
So you have 0, 0, 1, 1 is all gates. Then how about this guy?
None. What's your one?
This is none.
Wait.
None. It's none. One and none and opposite of none.
Yeah, this is none.
So how about this guy?
Maybe something like the one you didn't talk about.
Exclusive vote.
The one you didn't talk about.
That's
1, 0, 1, 1, 1, and.
So what can you observe?
There's no 0, 0 here. Why?
You don't have 0, 0. There's no 0, 0.
Maybe they made a mistake.
No, we are
They are
considering.
moving from there.
This is what we are doing. This is not arbitrary value. These are like your inputs. These are not arbitrary value. These are based on what you have here. So my point being that you can see how these perceptron, how they relate. Like by bringing them together, you can use it to solve this problem. And basically, what this is introducing non-linearity into your. By bringing in non-linearity, you can have a decision boundary that can split your data, that can generate your model. Basically, that's what I'm trying to say.
Is it just me? But
It is the output from
this is 0, 0, right? Like x1 and x2 is 0 at this dash there. Right? Like, yeah, that's x1 and x2 are 0 here. Right? Yeah. So why
That's
you
it
just
here.
yeah, but it's
no,
not
no
here.
issues. Ignore this part. This part is it, as is a relationship between when you bring these two guys together, you get this part. I don't know whether you
Okay,
understand. So
okay.
ignore when you bring this guy. Look at the weight and bias is 20
Yeah,
20.
20.
Then bias is
Yeah.
30. You understand?
Yeah.
So these are your inputs. 0 0. This 0 0.
Yeah,
Right?
yeah.
What's here?
That is 0 1.
0 1.
Yeah.
0 1.
Then
0 1.
yeah.
What's here?
That's 1 0.
1 0. So what's here?
That's 1 1.
So makes sense. Any question? So this is my point. With this, you can have a decision boundary. One of them is responsible for this, the other one is responsible for this. So these are what we call hyperplane. Yeah. By drawing this hyperplane, it's your decision boundary that you use to basically that's what decision boundary to separate the different classes. So if it falls inside, it means that it is the data is the green part. If it falls outside, is the red part. But with one perceptron, with one you can't do this. But with two, you can do this. So you understand why you need multiple layer perceptron. Yeah. So do this at home if you want, but you should. So let's come to
Yan Likomo.
Yan Leko. So this guy is the current director of Facebook. So this is this guy that is responsible for all your addiction, your Facebook feed addiction. Why you can't leave Facebook when you spend like 30 minutes on Facebook or 2 hours on Facebook.
But I'm not addicted anymore. It's not just
I know you're not addicted because you have Twitter that is making you addicted. So we should look at the guy on Twitter. So no, I'm being biased. So in 1998, while he was working for Bell Lab, so in Bell Lab, I think Bell Lab is more or less like how Google is now. Back in the days, we have like, there for me, we have Bell Lab, I think AT&T Bell Lab. Then another organization that looks like Bell Lab was another organization that looks like Bell Lab. Let's put Google. I just skipped one. Okay, IBM, yeah.
Amazing.
Show that organization again. Microsoft, no.
Amazing.
Apple, no. I'm talking about guys that really contributed to.
Well, yeah.
Let me not use the word open source, but they had like a lot of impact. Okay.
Microsoft, not Microsoft.
Not Microsoft. Microsoft is.
They only became open.
It just
quite
became open recently because they discovered that they can't continue living the way they are living. So, Linux. Linux has been open. So my point there is just that Bell Lab was like one of those labs that they gathered different people from different departments, different specialties. And what's did you? Yeah, fine. So what I can say about this, because sometimes just like I don't know how many of us listening to Jesse's quotes on stuff on yesterday. So he was saying something about the reason why he is regarded as the Chuck Norris of computer science. He has done a lot of projects in Google. He has done like just name any project. He has done it. So why the reason why that guy is that good is because first of all he's an open kind of guy. He has set different kind of challenges. But one of the major things there is that sometimes when you are in a field and you really want to know about that field, you just don't go online and start downloading tutorials and yeah, you should do that. It's good. But sometimes for you to like bootstrap or for you to like listen your learning process, get a mentor. Get somebody that is already doing that stuff there. Talk to the expert there. No, I'm not even. Get someone that knows what's actually happening in that field. They will like speed everything up. They'll tell you what you should concentrate on and what you should concentrate on. So back to Jeff Dean, he said something that, and if you really want to be versatile, if you really want to if you really want to increase your creativity, you should get the experts that are in that field. Get to know about them, get to know the kind of problem they have. Try to look on how you can bring what you know to that problem, to solve their problem. But basically what he's trying to tell you that if you are going to have about 10 research papers to read, don't read one. Read the 10. Have like an overview of the 10. If you really want to, if you have that, if you really, at the end of the day, if you really want to solve a problem, by having that broad overview, so when it comes to the time of solving that problem, you go back and read that one you want to read. But it's whenever you concentrate on just one paper, you are missing out on a lot of other stuff. So it's more or less about breadth versus depth, exploration versus exploitation dilemmas with respect to reinforcement learning. So my point there is sometimes it's good for you to your breadth you should go to do different stuff. That's my point. Like, to different stuff, especially when you're young, try to do different stuff. With time, try to like converge, like to lower your learning rate, to converge to your local. So same thing happens to Jeff. He did carpentry, he did physiology, he did psychology, he did computer science, and looking at what he has done so far, it's because he has been exposed to biology. That's why he could relate biology to artificial neural network. So that's my point. My point here is that it's very good for you to explore different points. But sometimes when you're exploring, you should be very, very careful. So you won't be exploring like a mad person. So you should just explore with. No, as a young person, what people don't seem to understand, sometimes you don't really know what we want to do. No, there's nobody who all this one you go to school must be a lawyer. Like, let me just give you an example. In my own situation, okay, I actually wanted to be a pilot. So then I did my IT with Nigerian Air Force. Then I discovered that, man, that is a joke. Okay, I'm running out of time. So my point there is that I discovered that it was not really making, this is not what I really want to do. So by interacting with the guys there, I discovered that, man, this is not what I really want to do. But if I was like outside there, I want to be a pilot, I want to, I never can tell, maybe I'll be a pilot, but I like where I am now. So my point there is just that it's very good to explore different stuff before you start converting. So this guy now worked with Bell Lab, and in Bell Lab he met a lot of guys that are interested in neural networks. So all together they worked with, they built the first convolutional neural network that was used for solving and character recognition. So by these are like different layers. This layer 1, layer 2. It's a 5-layer network. So
Excuse me, how many slides?
I'm true.
That's how you used to say when you were.
I'm true, really I'm true. This one is just stop talking and I'll run my slide. So you have your inputs. In the future we'll talk about convolutional neural network, but it's something like neural network, but again you have what we call kernels of interest. So you run your kernels around your inputs. Gives you a better representation. So you can see here in the first layer, you have this is what your network looks like. In the second layer, this is what your network looks like. You are getting like better from lower level feature to middle level feature to high level feature. So at the end of the day, this is what you are getting. So basically, this is the first application of neural network in the industry. This is what, because normally it's very difficult for humans back then to pick letters and look at it. Oh, this is the postal number of this guy. Put it here. But with this, coupled with this is what we use for OCR, optical character recognition. Coupled with that, use it to classify. They look at it. Oh, this is where this letter belongs to. So all these things was just to minimize human interaction and to make the work fast and to save the company money, a lot of money. So the same thing, okay, multiple classification. So in multiple classification, what you basically do is, in this situation, there's what we call one-hot encoding. Your data, you want to encode your data in such a way that pedestrian is 100, your car is 101, 0, 1, 0. So in your vector, your column vector, you have just 1. Here, every other thing is 0. So you have just 0, 0, you have 1. Then let's say another feature might be, another input might be 1, 0, 0, 0, 0, 1. Then another one might be 0, no, this is not 1 and 2.
That's for the output value, right?
That's for how you encode your inputs. So by doing this, basically by doing this, what it's just trying to tell you that if you should see by the pedestrian, let's call this thing something, let's not call it pedestrian, let's call this one car, let's call this one motorcycle, let's call this one truck. So if you should see 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. If you should see this represents car. If you see this represents motorcycle. If you see this represents truck. So it is checking the position of this guy. 0, 0, this is 0, right? 1, 2, right? So this is x, let's say this is x. This is x, x2, right? So this is x2, this is a scalar value. So this is not a vector, this is a scalar value, but this is a column vector. This is a column vector. So this is the point. My point there is that you encode your inputs, one hot encoding, then you train your neural network. By next week, you get to know how this stuff works. So my point there is you, and by doing that, when you do that, your output, you're not just going to, you know what we have been doing so far, you have only just one output, right? But here you're going to have multiple outputs, depending on the amount of class you have. If you have motor, it's going to be 1, 0, 0. If the activation function, if it's going to activate the one for motor, you're going to have motor. If it's motorcycle, you're going to have 0, 1, 0. If you have truck, 0, 0, 1. Makes sense, right? So if you're going to do real value classification, real value, if you want to output real value, you have just one output. And depending on the kind of function, whether you're using sigmoid function, because I said if you should remove the sigmoid function, if you should remove the activation function, you're going to have what? Then you're going to have linear classifier. But if you should put the activation function, you're going to have non-linear. So from there you can do logistic regression. But what here you are doing what? You're doing logistic regression. But this time around it's not just, you're doing multi-class multi-classification. So you get this point, then you run it through your softmax function. So by next week we get to talk about softmax. So let me just talk about perceptron. We all know what perceptron is. So I'm supposed to go through why this guy is there's something here. So why this guy is still loading? And it's still What's Francis? Papa, who is Francis?
I don't know whether they are
After the break, yes, it's Lawrence will talk.
Well, you know that I share your things to that maybe it's right now.
So at the end of the day, we'll get there. I've not organized this like very well. Okay, this is where we are now. So I'm sure now. I'm sure I will just rush this one. So. Yeah, I'm true. So this perception, you all know what perception is now. So you understand what this thing is, right? Impute weights, you understand it now. So why do we need it? Why do you need the activation function? So that is what it is. This is what you can do. This is what you want to do. Then it introduces non-linearity. Then you understand this. Then we did this, right? This is your AND gate, your OR gate, then your negation gate, then multi-layer perceptron. Why you need multi-layer perceptron to solve your XOR problem? Then this multiple layer perceptron. Then this is that's
Thank you.
That.
Hi guys, how's it going so far? Before we start the next session, we kind of like have to start almost immediately. Like we have our lunch right here while we set up and try to not get so distracted, eating the small chops and listen to Lawrence give you talk. But while we serve the lunch, I would like to introduce Simon. Simon, you've not met Simon. I don't know, some of you might know him, but you've not met him physically yet. He's one of the core organizer for AISF, and it's actually the reason why you've not started your project yet is because the project supervisor ran away to Abuja. Sorry. So he was in Abuja for the past month. He started AISF Days Abuja with them as well, and he had a class like that for a month. So he's a fantastic guy. I'm very happy to introduce him to you. When he's here, you're going to see him talk more than I do. Like, I like to push everything to him to talk about. So I'm really glad that he's here, because I don't have to talk about it. And also, Kelechi is like one of the godfathers of very high standard. So it's the bad guy, he's one of the bad guys. You should always connect with him. He likes to stay low, but it's fantastic as well. So I want him to, we've been working on the project. Sorry. So I want Simon, while we share the lunch, I want Simon to talk about, one other thing before I introduce Simon. We have in our midst two amazing people, great minds. They are from AI Commons, and I don't know how much of AI you do on Twitter. You might have come across them one way or the other. So I don't want to give a spoiler. I would like them to introduce themselves to you by themselves. But before they will come in, I think after Simon, kind of talk about some things and projects we have lined up. Then we can have Lawrence start this class with you guys. Okay, so use one mouth to one ear to beat while Simon talks. Yeah, so Simon, guys.
Alright guys, good afternoon. My name is Simon. Okay, you know. I'm a shy person, but just bear with me, I'm very shy. So I'm happy to be back to my community. This is my community. That community, they just borrowed me for 1 month. So I'm finally back. So greetings from Abuja. They are all happy that they are part of this groundbreaking community or what we are doing. So they said I should meet you guys, and once in a while they will be coming into Nigeria, one of them or two, so they always visit us. You know, they'll be coming to Lagos. Sorry, they'll be coming to Lagos. Don't mind me, I want to jam. I'm thinking about it already. Yeah. So this is the 6th week, and the first question I asked Tayo was, how far are people dropping? He said, people are dropping, but not like last month. These people are stubborn, they don't want to go. So it shows that we are all really enthusiastic about what is going on, and you are really interested in knowing AI and applying AI. So my job here is to make sure that there are projects we are doing. We're not just learning, but we're actually implementing. Okay. So there's a project we started some time ago. But the issue we have with the project is data. I know data is like the backbone of artificial intelligence and machine learning. So we've been trying to gather data for a while, and it's ongoing. So I want to introduce this to you guys so that you're also part of it in the data gathering. And at the end of the day, we're going to use that data to build something very wonderful. And it's called ChowNet. Have you heard of ChowNet? Have you heard of ChowNet? So ChowNet is very simple. Simple. What you are eating, food classification. ChowNet is just to classify food. Most especially our local dishes. Are we together? Now, if you're wondering, what do we want to classify local dishes for? What's the use? Well, it's just a foundation. There are a lot of things we can do from just classification of food. Can extend that to a lot of things. But the first thing we should do, the computer should be able to say, this is afam soup, this is egusi, this is spaghetti, this is chicken, this is, you can classify it. You can classify that, and you can do other things with it. Are you following? So, we are gathering data for now. We have different people will choose what they want to, the kind of data they want to provide. Some say, okay, I'm going to look out for just chicken, some say fish, some say egusi, some say this, you know. So with time, you get to know where you can drop your data. You can get the pictures from anywhere, the images, you can get the images from anywhere. You can snap yourself. We actually created an app, an image capturing app. And whenever, before you eat your meal, just snap and send. So we are going back to that app. We're trying to put one or two things together to make sure that it works seamlessly so that we can all be part of it. So at the end of this cohort, it's going to be our final project. We're all going to actually code this. Are we together? That is one. Secondly, as individuals, I've been following the group chats, even though I've not been saying anything. We're monitoring spirits. We're monitoring what people are saying and all that. There are people already doing stuff personally on their own. And I'm so excited, I'm happy. That people are actually doing stuff. People are asking, how do I clean this data? How do I do this? How do I, people who screenshot their work. One guy said that, come on guys, we started all these things together now. You guys are already doing this. It's part of it. If you sit back and do nothing, others will know. And when opportunity comes and you're not ready, you'll be able to grab those opportunities. So the idea is, we're going to make data available. I personally, I'm still trying to settle down. Different data available, make it available to us. So you just pick whatever data you want to pick and you do whatever you want to do with it. At the end of the day, you tell us this is what you want to do. But we also advise that you should collaborate. So I don't know what we're going to do at the end. Maybe we're going to share this class into groups. But start making friends, start grouping yourself on your own. You can pick 1, 2, 3 persons. Okay, guys, let's work on this data set. What can we do with it? Like that. Start doing stuff on your own. My job is that whenever you have any issue about, data sets, or you want to go on a project, you can just meet me or discuss about it, and know how to go about it. So thank you very much for having me back. I'm very happy to see this crowd.
You see why I like it? I didn't need to say time up. You understand that this is why I'm here is because the time is up. Yeah. Alright, please let me introduce John and Moses Olafenwa. Yeah.
Hello everyone. Yeah, it's very nice to meet you. I'm John Olafenwa, and it's my brother, Mr. Olafenwa. From here I come. I must say, it's a very special day for me because I first of all learned about AI Saturday I think early this year, and I was like, wow. So we have in Nigeria people who come together, and especially something was very fascinating. That's the fact that it was led by a female. Now, she told me the other time about Black in AI because we're also members of Black in AI. And I think one of the major things we used to be worried about is not having enough females. And I think I'm happy there are many females. Yeah, even though not yet enough, I would like to see more. But to see that people who come together like that, organize themselves, self-learning, without really being able to afford very expensive AI education, which is available in more expensive universities. And I think that's very correct. So I'd like to just tell you all about my work, the things we've been doing are really at AI Commons. First off, what we're really working on is to make artificial intelligence easy, right? The field is very amazing, and there are so many important things we do it. From image recognition to object detection, and some of you must have heard of generative adversarial networks. I'm getting by Ian Goodfellow, and it's a really cool technology really, that you could be able to just write a text description of maybe a blue house, and it could just generate an house like it without even you doing 3D at all. These are kind of stuff you could do with artificial intelligence. So when we went into the field, we realized that there was a lot of difficulty, technical difficulty into getting it. And while most people are really trying to break through the challenges, the tools to empower them to be able to easily do state-of-the-art artificial intelligence is often out of their range. Most of them are too technically difficult. A lot of you have used a number of different tools. But when you want to go beyond really MNIST, CIFAR-10, and do something more cool, it really becomes difficult. So one of the things we did is we created a framework, ImageAI created that, and he's going to talk to him about it. But then I created a framework called Touch. It's based on Facebook Python. How many of you are familiar with Python? Yeah. Now Python is more like TensorFlow, but it's built by Facebook and really it's very good to start. So what we built was a framework like the Keras for Python that will allow you to do more advanced AI. So let's say you've heard about capsule networks by Jeffrey and you've heard about GMs by Ian Goodfellow, object detection and all of these advanced technologies. And you want to use them, you want to build systems. So many of the frameworks that we have at present, they only provide the base functionality, right? They don't provide specialization like we say. So what we built is a framework that will allow you in very few lines to easily build systems with all this specialization. Think generative adversarial network is very difficult to train, highly unstable if they are not careful, even stuff like just changing the learning ratio to stabilize the whole thing. With this, you could just train in very few lines of code, like 15 lines of code. Highly optimized algorithms built directly. So, but today, you could get information about all of this stuff by checking our website, AICommons.science. Oh, AI Commons.science. Or just search Touch Fusion on Google, or search my name, and let me write it for you. Good on. Okay, good. Alright. Small letter. Alright. So you can find a lot more on it because I know time is not in my side. But I just want to tell you all before I leave with my brother. That is the very first phase to really becoming great in this field especially, is to believe in yourself. That I must tell you this, going into the field, I wasn't really quite a mathematician because really we were both developers programmers. And the field was very difficult, very difficult. But if you believe in yourself, that there is no eyes that you cannot reach. When you look at all these AI experts all over the world, from various universities in Canada, in the United States, in China, doing a lot of cool things, breaking new ground, making papers with thousands of citations. And when you look at the background, sometimes it can be intimidating to look at. Many of them have PhDs and have gone through a lot of internship and mentoring. But even right here, where you are, if you could focus your time fully, commit yourself with every bit of your mind to all this that you are learning, and dare to build great systems. Because I tell you, you can learn for 10 years, but if you decide to build something great in 1 year, what you actually be able to do, the skills you acquire by the end of that 1 year, will be more than just looking for 10 years. So really my advice for you is, look for a project. Look for an advanced task in different, not just image classification. Everybody can do image classification, really. It doesn't do. Look for something very advanced. Maybe it's Capsule Network, maybe it's AutoML. Focus your time maybe in the next 3 months and try to implement it using maybe TensorFlow, Python, any framework that you like. By the time you're done with it, publish it on GitHub. And you're going to see by that time that you'll be standing shoulder to shoulder with the giants which once believed you can never reach. Thank you all. I'll leave it over to my brother.
I'm grateful. I'm really excited to speak to you now because 20 minutes ago it was a bit dull, right? But everyone is excited. Okay, my name is Moses Olafewa. I'm the CEO, co-founder at AI Commons. As I said initially, we are trying to make AI accessible. And what we are trying to do basically is trying to make artificial intelligence easy, more or less a developer experience. So when you consider software development without IDs and SDKs, it was like that before, but eventually something came and made it very good. And that's exactly what AI is like. AI is possible, viable, commercially viable, it's working, but it's difficult to really implement or take to production or production. So that's what we're trying to do at AI. So, like I said, we created Image AI. It's for Python developers. And when you have to write thousands of lines of code and implement the algorithm and understand the algorithm yourself after installing TensorFlow, OpenCV, ESPN, etc. Once you install Image AI to Git, you can just with 10 lines of code, run object detection on 80 different kind of objects, or even train a new recognition model using this one. You can find out information on AI Commons site. So I won't talk much about that as we don't have much time. But yeah, I said one more point. I would like to add 2 more points to the things Number one is belief. We have already emphasized that. The second is to take up a tough job. In Nigeria, there is an unemployment rate, right? Everybody knows that. We study marketing, law, finance. But can someone tell me a pharmacist or a doctor who is unemployed that he knows Nigeria? Or a doctor, yes, who is unemployed? Do you know why? Because it's hard. And whatever is hard, only the bold can do it. So you want to make an impact, as far as you believe you can do it, take up something difficult. If it's difficult, like most difficult, that's why you should not back down. That's why you should do it. Because if you do it, you'll be a champion. So because you're trying to be a champion, you're trying to achieve a task, it's going to look like difficult and say, I can't do this. Don't say that. That's why you should do it. Because it's most difficult. As far as you speak your honesty, that's why you should do it. That's the second thing. Believe and take up a tough challenge. Take up a tough challenge, and when you do it, you'll be a champion. Now the third is sacrifice. You can't solve a tough challenge without sacrifice. That means walking through it. Sleeping just 2 or 3 hours every day. I've done that throughout this year. Most of the time, I get to sleep like 3 hours. It's like I was a day I tried to walk from one day to 10:30 the second day, and I slept the second morning 10:30. I didn't know I'm going to get here right now. But I'm here. But just believe it can take 3 months for someone, and it can take 2 years for another person. But just keep your belief alive. Take up a tough challenge. I'm ready to make the sacrifice. It might be sometimes being alone. Besides, how many of you are familiar with Stark making it in a cave? Tony Stark, Iron Man.
Yeah.
What is the first version? He made his most incredible invention in a cave. So don't say, oh, I don't have the electricity, I don't have the data, I don't have the powerful computer. As far as you have something, make use of what you have. Even if you're just only using it, you make great things. We put them to all challenges. And challenges is what brings innovation, not confidence. If you are comfortable, trust me, you will not be inspired to create something. But it's program that make you create something else. So you should do that. And we are, apart from the media and construction, we are developing a commercial application that can allow you to deploy AI very easily instead of installing TensorFlow and Keras and all of that. All you just have to do is to be familiar with Docker. For those who are familiar with Docker, we're going to provide all the necessary videos and articles to guide you through that. So once you install Docker and install the AI server, you can have an AI server completely on your computer, working completely offline, come with all sorts of computer vision features. Just like think of IBM Watson or Microsoft's Azure Cognitive or Google Cloud on your system. So that's what we are working on, and that's what we are building. And our intention is to release the first version free of charge to 500 people. So we sent out the survey yesterday. We already have a number of people. We surveyed from US, China, Israel, Singapore. I've discussed with Lady Tejumani, and I had the permission to tell you that everyone here gets the free version free of charge. It's still in development, but I can tell you that this is 3 months from now, you get from us. And we're going to create a Slack group, so we don't just keep it to you, but we are well connected. Anytime you can provide with us, you can provide support, answers to questions privately or publicly so that everyone can benefit. So eventually, when we have a second version, like 5 or 6 months from now, all of you can get 50% discount from this. We want to push it. So, with that, thank you.
Sorry, let me say my mouth. It's such an honor to have you here, and I mean, it's like great to Indaba and Jeff didn't tell you that you get a free GPU and free CPU. You know, it's cool when you get all these things, but you also know that you really need to up your skill set. I mean, what's the essence of having something, a very, very important thing, and you don't even know how to use it, right? So you've been challenged that you're going to get, I mean, we're trying to make life easier for you. You don't have to deploy this, you don't have to see your computer does not run on GPU, you can't be able to do blah, 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 and do. But now, how do you make sure to use this tool effectively? And we're even lucky to have them around. I mean, it's just to walk away to their office down the line. And I have this problem, I don't get how this works. You know, you don't get to do all that all the time. Without further ado, we'll start the next class. Thank you so much for coming. We really do appreciate it. And thank you for the generous offer. You can wait. All right. So, we start the next class with Lawrence. Everybody, Lawrence. Hope you enjoyed the class.
Thank you, George. Pack your things and go. About to start the next. So we're about to start Act 2, Scene 2.